this lecture today is actually sort of setting up a problem. It's going to set up the infrastructure of what we're going to do actually for a bit of time now after this. And it's going to be also the start of what homework 3 is and beyond. Okay? Okay, so that's the comment there. Final, when I was walking in here this morning, sometimes you wonder, like, am I having any impact in this life at all? You might wonder that. And what was so great is I'm walking in and I see one of my old 301 students from last year, and he just gives me, and I feel like I've had an impact. That was a forearm shiver, by the way, just in case, because we talked about it last time. I was a little bit upset about that so many people didn't know what that was. But you see, after a quarter's worth, they know it, they just do this, and I know, it's like a connection. I got a little teary out there, and then, but I've recovered, and I'm ready to just deliver some more smackdown, because I know I'm having an impact in the best kind of way. All right, so today we're going to talk about the setup of a problem that I love to do because it illustrates so many of the computational issues that you have to deal with in practice. So let me draw a picture first. And here is the picture we're going to look at. We are going to look at some kind of fluid. So for those of you in atmospheric sciences, oceanography, you'll be so happy. Because what we're going to look at here is some kind of fluid, and we're going to look at shallow fluid theory. Okay? Shallow water waves. Okay? It doesn't have to be water. It can be anything. So you can think about this as the atmosphere, or any kind of thin layer of fluid or gas, as it were. So here it is. We have some kind of fluid here. There's important things that we want to understand here. So first of all, we say that there's maybe some characteristic length, L, that measures sort of the structures or dynamics that are happening in the XY direction. The fluid height itself comes in some characteristics, height D. Okay? And in addition to specifying location of the fluid, what we're interested in actually quantifying is the dynamics of the fluid. In other words, its movement. So we need the velocity of the fluid. Okay, so there is going to be a U, V, and W. So the velocity of fluid is in the X direction is U, Y direction is V, and in the Z direction is W. So our velocity field will be U, V, W. Okay? So we want to understand the motion of this fluid and try to compute this thing, because it's actually kind of a complicated system. We'll derive it, and then we'll talk about what's interesting about it from a computational point of view. One thing we're going to do here, and this is important, is we're going to make up a parameter, call it delta, which is this ratio of this scale here, the Z direction, the height scale, to the XY direction. Okay? And we're wanting this to be small. Okay? So where does this hold? Well, for instance, if you look at the ocean, right, if you think about how monstrously big it is, hundreds and hundreds and hundreds of miles across, yet its depth is what? Marianas Trench is how deep? Do you remember this from junior high? Like 7 miles or something kilometers to do conversion. I remember that. So you didn't want to fall off a ship there. Okay? Or you'd go down there and you'd die at 7 miles under the earth. And you'd be crushed, too, because it's like high pressure. Okay? But if you die in Lake Washington, you're 200 feet down. No big deal. They can like scrape you up. Okay? So, but there's this idea of this length scale separation between what this is and versus this. The atmosphere is something similar, right? So if you think about our atmosphere as a very thin layer compared to the actual size of structures we might want to look at. For instance, if you look on a satellite map, kind of over the, here I'll show you where. You guys all recognize that, right? And then you recognize things like this that kind of do that. Okay? So these things here are in hundreds of kilometers across, and yet the atmosphere is, you know, up to the, what, tropopause? Is that what you guys call that? Right? How many kilometers? Like 5 to 10? 12. So, yeah, see, thin. So there's a whole length scale separation here, right? But this is huge compared to its thickness, as it were, in the z direction. We want to capitalize on that, because what we'd really like to understand is how do these things move, evolve, and so forth. And we want to understand the dynamics. Okay? All right, so how do we go about doing this? Well, we have this picture here, and we want to take advantage of this scaling. And we also want to try to figure out how we would derive equations of motion for this. Now, in some sense, this lecture, you can say, okay, so what? You can delete it from your mind at some point, but this is just kind of just for educational purposes. And then when we get the equations at the end, that's what we're going to spend all our time on, and you maybe don't care where they come from. But the equations are pretty awesome in the sense that they give us a lot of cool computations to do. So I'm going to also define a quantity here called the vorticity. Okay? Usually, like if a bad guy is trying to destroy the world, he'll put it in a giant vortex or something, right? That's where we learn about vorticity. Like when you're a kid, where did you hear about a vortex? Because something was going to get destroyed in a vortex somehow, right? It just sounds awesome. Say it, vortex. It's like strong and powerful word like that. It's got to be able to destroy something. But what a vorticity is just as simply somehow the twisting of the fluid. Let's call this omega, not to be considered confused with W. And omega z is the vorticity that comes around from the twisting in the xy direction. Now, since this is going to be a shallow layer of fluid, we're not going to really consider vorticity in either the x or y direction. Just sort of from the top view, if I look down on this fluid, what is its twisting motion? A lot like that hurricane that I drew in the Gulf. Okay? How is it defined? Well, the way we define vorticity, this vorticity what we want to look at, and we're just going to call this omega z, and we'll just call it omega because that's the only one we're going to consider. How it's defined is the partial, let me write it down here, the velocity v in the y direction, its rate of change is a function of x, and the velocity in the x direction and its rate of change in the y direction. And this is telling us some about the twisting of the fluid. So high vorticity means you have a lot of rotation of the fluid. Low vorticity, very little. Okay? So we're going to define this quantity. And what we're actually end up going to do at the end of the day is write everything in terms of the vorticity dynamics. Okay? So how do we get some kind of equations of motion for the system? Well, we're going to do two things. We're going to look at conservation of mass and conservation of momentum. So pretty simple concepts in some ways, but they can give you some very nice results. So we're going to consider a little box in here. Okay, I'm not going to draw it on it. Okay, we have some little box of fluid. Okay, and I have an x1, x2. This is this x direction, and then this is y1, y2. It's a little pillbox, and what I want to understand is the mass, the dynamics of the mass in this little box. Okay? Now the mass itself is simply, what I do is I say, okay, to calculate the mass, I integrate over all the stuff inside there. So I have some density. Oops, sorry. Times the height, dx, dy. So, you know, this is the height, h, is the surface height, and it has some density. So I take whatever the density is times its height, integrate over this little box area, and that gives me the mass in there. And what I'm interested in is not the mass currently there, but what I'm interested in going to be is how does the mass change in time? Okay? Now, if we consider a fluid that's not moving at the speed of light or something like that, which is generally the case in the Gulf, So you don't have any kind of E equals mc squared stuff. So none of the mass doesn't become energy somehow. Then the mass is going to be conserved. And all you care about is how do I then describe its dynamics? Well, if you look at the rate of change in time, you look at the mass in there here, how does the mass change? Well, you can calculate it by saying, well, I have some mass, and then I can calculate the flux of fluid coming out or into this box on these different surfaces. Okay, can you visualize that? I should have given you all Costco 3D glasses, and then you could just totally like, oh yeah, there they are, the arrows they're all pointing outwards, and you just say, well, if I have fluid coming in, it's going to change the mass. If I have fluid going out, it's going to change the mass, and so forth. So I can calculate the mass flux, the flux of mass coming in and out of that box, plus the mass already had in there. And what you're going to find then is the following. If I look at the change of mass, or the rate of change of mass, first of all, I can calculate what's in there already. And I'm going to do one thing, by the way. I'm going to assume for the moment that the mass, rho, is constant. The density is constant of this fluid. And so I technically would have a rho here, but all the terms I'm going to have are going to have a rho, and they are going to drop out because this rate of change of flux of mass can be equal to 0. In other words, mass coming in and out, conservation of mass says that the total the concentration of mass can't change. In other words, you can't just have stuff disappear. Okay? So it's going to be all equal to 0, and the rho's all going to cancel out. So it's going to give me this quantity here, plus what I've got to calculate is what is the flux across the two boundaries, y1 and y2? And what is the flux of mass across the boundaries x1 and x2? So what is it? Well, so first of all, across y1 and y2, if you look here, so we're going to integrate across this surface here and ask how much is coming across this panel. Right? So I have to go to x2, and I have to integrate it from y1 to y2. So that's where the integral from y1 to y2 is. And I say, okay, let me calculate how much stuff is coming across this whole panel. Okay? And then I'm going to do that from here, on the other side, on this side, and this side. I got 4 sides. I got 4 things I got to calculate. 4 panels to calculate how much fluid is coming in or out. Okay? And normally what you do is you put an outward normal there to say everything's going, that's your standard definition, is you say an outward normal to the surface, and then you calculate. So plus signs means here it's going out, and then minus signs coming in. But then it changes on this one here, right? This side is the opposite sign convention. If your arrow is going out, the minus means it's coming in, plus means it's going out. So when you look at this thing, if I integrate across that first surface, I can get the following. Said, this is not going to be on a test like the derivation of this or doing stuff like that. We're going to solve equations. So this lecture is just purely for your enjoyment. And hopefully you are just enjoying it immensely so far. Okay, but there you go. Little derivation. You go over here to the surface x2. You say, I have u x2. And what is u? It is the velocity of the fluid in the x direction at x2 times the height. Remember, it's times also the density if you want. We're going to take that out. So that is how much fluid is flowing across here. Right there. So I'm at x2, and I'm integrating across this whole thing on this whole sheet right there. And here, the velocity, right, is u at x2 yt. That's the velocity across this thing. Now notice on the other side, here at x1, I have the opposite sign convention. Okay? So fluid flowing this way means it's coming in, going out. It's going that way, it's going out. So it's the opposite sign convention to my arrow. And that's why we have the minus sign. So when I come over here, I say, go to this thing here, look at x1. calculate the velocity across that surface times the height, integrate it up, and I have now the flux across two surfaces. Okay? And then I can do the same thing now on the y surfaces, so where y1 is and y2 is. Now I can calculate the fluxes there, and this is what you get. Vx y2 t hx y2t minus bx y1t hx y1t. Okay. Equal 0. There's your conservation of mass. Okay, now a couple things to notice. Now you may not see this right away, but I'm going to tell it to you because actually it works out beautifully for us here. Do you guys remember the fundamental theorem of calculus? Remember, we keep doing all these really, hopefully, simple things in calculus. And here's what it is, right? It says that right, something like this. You could do this here. Right? You undo the integral. You get this thing out here. So you evaluate it at one endpoint and at the other endpoint. Now what I'm going to make a connection with you here is that this is a fairly simple result from calculus. But now let's go look at what's in here. Here's the value of this function at x2 minus the value of the function at x1. This here looks a lot like my yb minus ya. So I could take this and rewrite it in an integral form like we have over here. So I'd say, okay, since I have x2 and x1, I could rewrite this as an x derivative inside of an integral. Now why would I want to do that? I'll show you why in a moment. So let's go ahead and take this thing and use this fundamental theorem of calculus. And, oh, this is sweet. Check this out. Okay. Nice. See my fancy board work? I didn't know I was going to do that, but now I am. What does this become? Well, so first of all, I still have this y1 integral, y2 integral, dy. Now, what do I do with what's inside of that thing? Well, I'm evaluating x2 minus x1. I can replace that with an x integral. So I can say, how about I replace that with x1, x2, d dx of u x y t h x y t. There's my function dx. I just want to tell you I haven't cheated. I haven't done anything wrong. Everything's good so far. Everybody good with that? Similar thing can happen with the other one. And this other one now, let's take a look at what it gives us. In this one here, what I'm looking at is the difference of this thing being evaluated at y2 minus what's evaluated at y1. So this fundamental theorem of calculus would tell me, like, oh, if I have something that's evaluated at y2 minus y1, I could rewrite that as a d dy of something. Right? So I could rewrite it as an integral d dy. So I'm going to do that here. So what I get here, then, is I still have this x1, x2. Now I have a y integral, and what I have is the y derivative that comes in. And I'm just write this shorthand like that. That's what I get. So I greatly simplified it in some sense. I mean, I still have two integrals to evaluate, and that might concern you a bit. Okay? But now, here's what I'm going to make the point about. I have this thing rewritten in two integrals, this thing rewritten in two integrals. Let's go back to this board here. So if I look at this, then, I could say, okay, let's go back to this board now. Let's rewrite what we have. In the first equation, I have d dt of two integrals there. In fact, I can take the d dt in. And so what I'm going to get is two integrals, x1, x2, y1, y2, d dt of h, dx dy, plus Now, what did the second term reduce to? The second term reduced to x1, x2, y1, y2. And that second integral reduced to d dx u h, dx dy. And then the third one, x1, x2, y1, y2, d dy, v. Oh, sorry, that was supposed to be v over there. Pretend it was a v. Nice thing is that u's and v's look pretty similar because I could always say, no, I have a v there. You're just misreading my handwriting. Okay. This is equal to 0. Where? No. This one here? No, it's d dy.
You're integrating the y1 first and then the other.
You mean switch this around?
At the end, we got dx dy. Dy.
This is a v here, right?
There you go. There you go. That dy, dx.
Okay, fine. Yeah. Doesn't matter.
Okay.
Yeah, so, all right. Okay. All right, so here you go. Now notice, this has to hold for all t, all x1, and all x2, y1, y2, all of it. Now the only way, now notice they're all integrated over the same thing. And the only way this thing can add together to 0 for all t, for all x, for all y, is if the integrand is equal to 0. And the integrand is that thing plus that plus that. So at the end of the day, with all that work, what we end up with is our conservation of mass equation, right, which gives us dh dt plus d dx uh plus d dy bh equals to 0.